In this lecture, we'll discuss about some examples for linearization. But before we proceed, to recapitulate, if x dot is equal to f of x, where x is in Rn and f maps from Rn to Rn, and suppose x star is the equilibrium point that we are considering, then the linearized model would essentially be of the form del f by del x evaluated at x equal to x star multiplied by the perturbation part. So this is what we have, and we label this partial differentiation as a matrix A, which was a n cross n real constant matrix. Please note that we are considering a autonomous system in this case. So how is this del f by del x written? So del f by A is equal to del f by del x evaluated at x equal to x star is for n dimensional system del f1 by del x1, where f1 essentially tells you the evolution of x1. Okay, so x1 dot is f1 of x. Okay, so let me put it properly. So x dot equal to f of x essentially means x1 dot is f1 of x, x2 dot is f2 of x. So x1 dot's evolution possibly depends on x1 till xn, x2 dot's evolution depends on again x1 till xn, till xn dot to be equal to fn of x. So that is what actually this means. Okay, so we have del f1 by del x1, del f1 by del x2, and this goes on till del f1 by del x n. Okay, so for the row you take f1 and take its parcel with respect to x1 x2 till xn. Now we'll move on to the second row, which is del f2 by del x1, del f2 by del x2, and so on till del f2 by del xn. So in the second row, the parcel of f2 is taken for all entries with respect to x1 x2 till xn, and we continue doing this till we reach the last row, which is the nth row, where del fn by del x1, then you have del fn by del x 2 parcel of f1 with respect, I should say, I think it is dou, it's not del, it's dou also. So with del fn by del xn, so these partials, n cross n number of partials that you evaluate, has to be evaluated at x equal to x star. So this is what is the del f by del x matrix, and is also known as the Jacobian. This is the Jacobian of f. Okay, now let us take an example. Example 1. x1 dot is x1 cube plus x2, and x2 dot is x1 x2 cube. Let's see what are the equilibrium points here, and what information would this linearization yield about the stability or instability of the equilibrium points. Okay, so for calculating what the equilibrium points are, what we do is we equate x1 dot to 0 and x2 dot to 0. So equating x2 dot to 0 tells me that either x1 is 0 or x2 is 0, and equating x1 dot to 0 tells me that x1 cube plus x2 has to be 0. So if you use these and finally solve, you get that 0 0 is the only equilibrium point that actually the system has. Okay, now we want to see whether the equilibrium point 0 0 is stable or not. So this is the equilibrium point, and we'll use the idea of linearization to obtain the stability. So what is the A matrix? A matrix is del f by del x evaluated at x equal to x star, which is 0 0 in this case. So it is del f1 by dou f1 by dou x1, dou f1 by dou x2, dou f2 by dou x1, and dou f2 by dou x2 evaluated at 0 0. So let us see what happens. With respect to x1, you have 3x1 square. With respect to x2, this is 1. f2 with respect to x1 is x2 cube, and f2 with respect to x2 is 3x1 x2 square, and this you evaluate at x equal to 0 0, which gives me 0 1 0 0. Okay, so please verify whether this is correct or not. If there is any mistake, then please do report to me. In case this is correct, then A is the matrix that we have obtained, whose eigenvalues are essentially 0 0, which means the stability of x star, which is essentially the zero equilibrium point, is inconclusive from linearization. Okay, now let us take another example. x1 dot is x2 and x2 dot is minus x1 plus x1 cube by 6 minus x2. So what is the equilibrium point? For that, again you have to do x1 dot to be equal to 0 and x2 dot to be equal to 0. So x1 dot equal to 0 yields that x2 has to be 0, and this yields minus x1 plus x1 cube by 6 minus x2 has to be 0. Now if we use both of this, what we essentially get is 1 minus x1 squared by 6 is 0. This is coming from the fact that x2 equal to 0, which essentially indicates that x1 is 0 or x1 squared is 6. And this x1 squared 6 implies that x1 is either plus root 6 or minus root 6. So what are the equilibrium points that we have with us? The equilibrium points that we have is 0 0, root 6 0, and minus root 6 0. So these are the equilibrium points that we have. We have multiple isolated equilibrium points in this case. In this example, I'll show you the linearization only about the 0 0 equilibrium point, and then try to conclude about the stability of the 0 0 equilibrium point. I leave it up to you to compute conclude about stability for the remaining two equilibrium points. Okay, so what you have is A to be equal to 0, 1, then have 0, then you'll have 1, then here you'll have minus 1 plus 3 x1 square by 6, which is essentially x1 square by 2, and then minus 1 evaluated at x equal to 0 0. So this gives me that this is 0, this is 1, this is minus 1, this is minus 1. So what are the eigenvalues that you get? The eigenvalues that you get here is for the characteristic polynomial lambda square plus lambda plus 1, which is I guess would be let's compute this, what the eigenvalues would be. And the eigenvalues would be minus half plus minus j square root of 3 by 2. So what you have here, that the eigenvalues, both the eigenvalues have negative real parts. Okay, so real of lambda 1 is less than 0, real of lambda 2 is also less than 0, lambda 1, lambda 2 are complex, which means x star equal to 0 0 is a stable focus. Okay, similarly try to conclude for root 6 comma 0 as the equilibrium point and minus root 6 comma 0 as the equilibrium point, and see what are the conclusions that you can draw. In the next lecture, we'll discuss on solutions, and we'll see certain properties that in the subsequent lectures we'll see properties that will guarantee the existence and uniqueness of solutions for a differential equation. So we'll stop here. Thank you.